Now, our next discussion is variation of pressure at the 2 points when the fluid is in horizontal acceleration. It means now the fluid is moving in a pipe from left to right or from right to left. So we have to consider their velocities and we have to understand whether the flow of the liquid is laminar or it is turbulent. So when the Reynolds number is less than 1000, it will be a normal flow. But when it goes between 1000 and 2000, it is laminar, and above 2000, it will be turbulent. So now we have to consider the variation of pressure in a horizontal pipe at 2 points. When fluid is subjected to constant acceleration, now when we speak constant acceleration, it means that is acceleration will not change. So different elements of the fluid orient themselves so as to obtain a new equilibrium position with respect to the vessel. Since the fluid particles are relatively at rest with respect to one another, therefore the laws of fluid statics are applicable, but in the modified form to take into account the effect of acceleration. Obviously, we have to consider the velocity. Now we are finding here in the given figure, that is a container is there, a movable container on the surface. Why we have taken a movable container? To understand the acceleration. In the fluid, we have taken 2 points. Heights from the top are given as HA and HB, and the length in which the pressure is to be estimated is small l. Delta S is the area around a point, A or B. Now, the direction of acceleration is indicated. It is moving from left to right. And now, we come towards another concept. Consider horizontally accelerating container with liquid in it. Take 2 points A and B as shown in the figure at horizontal distance L along the line of acceleration A. Take horizontal cylinder within the two areas, that will be delta S, towards or around A and B. The pressure at A is PA and pressure at B is PB. Pressure will be taken as force into area. So again, we are taking the forces along the line AB. One of the forces, the product of pressure and area, that is PA into delta S towards right, and product of pressure and area, that is again force towards left. As I've suggested earlier, when we take a horizontal flow, we have to take the forces on the right side as well as to the left side of the tube. So PB delta S, that is towards the left. Under the action of these forces, the element is accelerating. Whenever we apply force and mass is constant, it means body is accelerating in the direction of force. So PA delta S minus PB delta S will be equal to MA. That is the second law of motion. PA minus PB into delta S, that will be delta S LA. So now what we are finding, that from above equation, we have taken out delta S common, and PA minus PB means difference of pressure at the 2 points with area delta S. So this force is pressure into delta S, that is we can take delta S into LA. So P1 minus P2 will be LA delta S very small. 2 points in the same horizontal level do not have equal pressures for the fluid accelerating horizontally. If atmospheric pressure is P naught, then the pressure at A will be P naught H rho G. But we have taken HA, that is height of A or the depth of A. Rho is the density. And PV will be P naught plus HB rho G, as there is no vertical acceleration. H, A and HB are the depths of the points A and B from the free surface. H1 rho G minus H2 rho G will be equal to L rho A. So from this equation, we get the value of A over G, and A over G will be equal to H1 minus H2 over L, because rho will cancel off from both sides. Now, A over G is taken as tan theta. If we check the figure, we will find that A is operating like a perpendicular and G is operating like base. So A over G will be tan theta, and finally H1 minus H2 over L can be equated with tan theta, where theta is the inclination of free surface with the horizontal. Now, variation of pressure at 2 points when fluid is in vertical acceleration. So now horizontally there is no acceleration, but fluid is flowing vertically, that is from top to bottom or from bottom to top. Then what will be the acceleration? Now consider, again we are considering the 2 points A and B inside the liquid. So we have to consider liquid and we have to select 2 points. Point A and point B, we have to check up how much pressure are operating at point A and B, and both points are in the vertical plane. So they have a vertical separation H. So between A and B, the separation is H. Where the liquid is accelerating upward, that is from bottom to top, consider a vertical cylinder of length H with boundaries A and B. Delta is the surface area around the boundaries A and B. PA and PB are the pressures at A and B. And whenever we speak of pressure, it will be force over area or forces pressure into area. We will generally take into consideration the force, that is in terms of product of pressure and area. So, the next concept. Before proceeding to the next concept, the figure is to be checked. That is, there is a system in which we are taking A and B at 2 points in the fluid. Height between the 2 points or the distance between the 2 points is h. Density of the fluid can be taken as rho, and A and B are the 2 points within the fluid. P and PV are the pressures at B and P, and when we speak delta S, that is the area around the points A and B. And the system is accelerating upwards as shown by letter A. The forces acting on the cylinder are PA delta S upward, PV delta S downward, and W, that is the weight. Weight is mg, m is mass, that is density into volume, and volume is obviously area of cross section into height. So weight is written as delta S h rho g downward. Under the action of these forces, the liquid cylinder is accelerating upwards with acceleration a. Therefore, P delta S minus PB delta S minus mg will be equal to ma. And then we simplify the result to PA minus PB, that is rho into G plus A into H. Now, we consider some special cases. If A is negative, that is, we are referring to retardation. The vessel is accelerating downward, then PA minus PB, that will be rho into G minus A into H. Similarly, if A is 0, then pressure is equal everywhere inside the liquid, And the third thing, if A is greater than G, then fluid occupies the upper part of the container. Now we come towards the variation of pressure when fluid is under both horizontal and vertical acceleration. So horizontally and vertically, both accelerations are to be considered. Now it is slightly more complicated case. When fluid is accelerating arbitrary direction, arbitrary means which cannot be defined in any direction, then pressure varies both horizontally and vertically, separately for horizontal and vertical component of acceleration respectively. Now we are taking an inclined plane and the vessel is moving on that plane, and the components are taken as A1, vertical component of acceleration, A2, the horizontal component, and the resultant is A. That is the direction of motion of vessel. So, when fluid is accelerating in arbitrary direction, then pressure varies both horizontally and vertically, separately for horizontal and vertical components of the acceleration respectively. Now we take into consideration the vector calculation. So A will be equal to AX into I, that is, I is the unit vector along x-axis, AY into J, J is the unit vector along y-axis. So AX is A cos phi and AY is equal to A sin phi. Now difference in pressures at the 2 points on the same horizontal level is given as delta P is equal to L rho into AX. So we can write L rho and AX can be taken as A cos phi. And similarly we can take delta P, that is rho into G plus AY. For AY we can replace A sin phi. So after these calculations we come to the next concept. Inclination of the free surface with respect to horizontal is given by tangent theta, that is AX over G plus AY, or tan theta is A cos phi over G plus A sin phi.